In this video, we will learn about how integration is used to determine the ratio of nuclei in NMR spectroscopy. So for a typical proton NMR experiment, we are able to take the area under the curve of our signals, that's called the integration, and compare those integrations of all the signals to get to the relative ratio of protons that are being shown in the NMR spectrum. So for an example of this, we can look at the molecule ethyl acetate, which has those three different types of protons in a overall 3 to 2 to 3 ratio. So if I pull up the NMR data here, first of all, we should be able to expect that the red set of protons is a singlet, the orange set is a quartet, and the purple set will be a triplet. And we should also be able to predict roughly where these show up in terms of chemical shift. And that should bring us to the quartet here, singlet right here, and triplet right here, matching exactly what we need. The integration of this NMR spectrum should then tell us that there are 2 protons responsible for this signal, 3 for this signal, and 3 for this one. And so that's exactly what happens. I'm going to show you a few different ways that integrations will be shown to you. So the first way will be kind of through what looks like an actual integral symbol. And so what you'll see is kind of computer generated, these kind of S-shaped integral curves, and the height here is supposed to help you figure out a ratio. So the ratio of the red to the orange is supposed to be here shown to be about 3 to 2. Same thing for the purple to the orange, about 3 to 2. And the idea is that this is overall then showing you that red and purple have about the same integration here. So yes, you're supposed to take a ruler and measure this and compare against all the other integrations. Sometimes this is shown in a slightly different form where the various integrations are stacked on top of each other. So something like that, where you can kind of see the red and the purple pieces, but instead of just all being at the same level, they're kind of added to each other as you go up. And this allows you to get like kind of the total sum of protons. More modern software will just show you a number, so it might tell you that there is a 3 to 3 to 2 ratio like so. And another way that you might see this data is kind of reported as it is in a scientific manuscript. And so when that happens, you give a little bit more information like this, where the chemical shift is given in addition to the splitting pattern, the J value for that splitting, and the number of hydrogens that this signal is being assigned to. So 2H right here. A very important thing to keep in mind is that the relative ratio of integrations is not necessarily indicative of exactly how many protons there are in the molecule that is responsible for the NMR spectrum. So a good example of that is this solvent molecule here, MTBE, or methyl tert-butyl ether. If we're looking at this, we should see there are 3 hydrogens for the methyl group here, and there are 9 total equivalent hydrogens because there are 3 methyl groups that are equivalent here. So that means we have a 9 to 3 ratio of protons, but NMR software has no idea whether it's 9 to 3 or 3 to 1 or any other ratio, 27 to 9, etc. Right? So if we're looking at the data, what you would see is there is something with a relative integration of 1 to something with a relative integration of 3. So again, the key point here is that this 3 to 1 ratio is just a ratio. It is not the absolute number of hydrogens. And one tempting thing to do is to look at this and say, because this is 3 to 1, that means I have 4 total protons. That's not necessarily going to be the case, right? Because this could also be 9 to 3, which would be responsible for 12 total protons. Right? So that's just something to keep in mind when interpreting data. Another question that comes up is, well, why don't we talk about integration when it comes to carbon-13 NMR? Well, there's more complex reasons behind this, but part of the issue is that because carbon-13 is such a more difficult nucleus to probe by NMR, it's done experimentally by kind of transferring magnetization via the proton spins. And because of this whole transferring process, the integration information is lost. So you don't get the same amount of signal back because different carbons have different numbers of hydrogens attached to them. So generally speaking, the more hydrogens attached to a carbon, the more intense its signal might be, but that's a very broad generalization. So I do have an example here. So this is 1,3,5-trimethylbenzene, which has 3 different carbon atoms by symmetry. And we would expect those to show up in a 1:1:1 ratio if we were able to do integration. Right? Of course, if you look at this top row here, this is the carbon NMR data. We don't really see kind of 3 equally sized peaks. And that's because we're not getting absolute integrations for carbon NMR. Just to assign these peaks here, we should expect that the assignments go like this. So one more thing about this spectrum is that there's 3 small peaks right here that you may notice. These are not from the analyte. These are coming from the solvent that was used to prepare the sample. It's a common solvent, which is deuterated chloroform, or CdCl3. And the carbon is showing up at this signal. And so this is another way to do a reference, because if you use a standard solvent, then that solvent should always have the same chemical shift to which we can reference our analyte's chemical shifts. So the point of this video was just to go over the fact that we can do integrations in proton NMR, and that those integrations can help us figure out how many protons are contributing to a signal, which then allows us to correlate that back to structure. And finally, that integration does not work for carbon NMR.